All right. We're in section 7.6 where we are going to solve exponential and logarithmic equations. Um, well, basically in the first portion here, well, in this section is that we are given a variable in our exponent. So if we can determine that if their bases are the same, we don't necessarily need that base anymore. For example, if we have 4 to the x power equals 4 to the 7th power, we can conclude that x equals 7. So if if we go to these examples here, I have a to the x power equals 64x to the minus 5. Now what I want to do is I want to get their bases the same. And I can because I know that a to the x can stay the same, but this would also equal a squared, all of which could be to the x minus 5 power. Okay, so if I were to then use the power rule, I got 8x here, which then equals 8 to the 2x minus 10 power. Now that they're the same bases, I can now solve for x. So I don't even need my 8 anymore. I can just say x equals 2x minus 10. Here I'm going to subtract 2x to both sides, which gives me a negative x here, which equals a negative 10. And so then my x here would equal 10. Looking at example B, I can say, well, I got 1/3 and I got 81. I know I can take 3 here to the 4th power, which will give me 81, and then I can tack on the 3 minus x power, which then equals, I can use 3 to the negative 1 power, which then I can then tack on to the 5x minus 6 power. Using the power of power rule, I got 3 to the 12 minus 4x power equals 3 to the negative 5x plus 6. Now that we've gotten the same bases, I don't need them anymore, but now I can just use the exponents to solve for x. So I can just go something like this. And I'm going to try to combine, x to one side, so I'm going to add 5x to both sides here to give me x here, and then I'm going to subtract 12 to both sides, so 6 minus 12, which gives me a negative 6. Okay. Next step is I want to be able to solve an equation by taking the logarithm on each side. So I got 9 to the x power equals 35. So first step is you're going to have to isolate the exponential expression. For this first example we did. After that, we can take the appropriate logarithms to both sides. So I know that this can be written as the log base 9 of 35, which then that'll equal x. Here, I can use my change of base formula. So I can say that x equals the log of 35 divided by the log of 9, which then x roughly equals 1.62. Okay. Going towards example B, I got to isolate my exponential expression. So I'm going to subtract 9 to both sides. So it leaves me with 3 to the x power equals 7. Rewrite this as a logarithm. I can say that this is log base 3 of 7, which will equal x. From here, I can take the change of base formula, so I can say log of 7 divided by the log of 3, and then my x here, by dividing that out, will roughly equal 1.77. Okay? Got a story problem. Using exponential model help me solve real-world problems. It says if there are initially 2,500 bacteria in a culture and the number of bacteria doubles each hour, the number of bacteria after t hours can be found using the formula n equals 2,500 times 2 to the t power. How long will it take the culture to grow to 75,000 bacteria? So n in this case is the total number of bacteria in any particular hour, whatever hour that is, and t represents those hours. So what we need to do is I need to find what n when n is 75,000, when that equals 2,500, and I need to find out what t is going to equal. Well, let's isolate my exponential expression. So I'm going to divide both sides by 2,500, which then just gives me 30 equals 2 to the t power. This can be rewritten as a logarithm, so then I can say that this is log base 2 of 30 equals t. So from here I can use the change of base formula, so my t equals log of 30 divided by the log of 2, which then this equals roughly about 4.5 hours. So within 4.5 hours, we're going to have 75,000 bacteria in that specific culture. Next thing we have is what is called the property of equality for a logarithm equation. So if we're given an equation with logarithms, and again they have to have the same base b, if we can conclude that it has the same base, we won't necessarily need the logarithms to help us solve the equation, because for example if we have log base 2 of 7 equals log base 2 of x, we can conclude that x equals 7. Okay, so from here we have log base 4 of 2x plus 8 equals log base 4 of 6x minus 12. So it has the same, we have the same base of 4. So that means that for this to equal each other, whatever this value is has to be the same as this value. So they have to be the same numbers. So basically all I can do is I can just say 2x plus 8 equals 6x minus 12. And by doing that, I subtract what? I'll subtract 2 to both sides, 2x to both sides. And then that gives me what? 8 equals 4x minus 12. I'm going to add 12 to both sides. It gives me 20 equals 4x. Divide that by 4. My x here will equal 5. Looking at example B, I got log base 5 of 3 plus 2 times log base 5 of x equals log base 5 of 75. Well, now I'm going to go back and use some of my properties of logarithms to help me out. First thing I'm going to do is I'm going to say log base 5 of 3 plus log base 5. This can be now written as x squared. I'm trying to condense this again. And now I have the addition one, so I can use the product property. So now I have log base 5 of 3x squared equals log base 5 of 75. So now from here, I don't necessarily need my logarithms anymore. I'm just trying to solve what x is. So I can write this as 3x squared equals 75. divide both sides by 3, so I got x squared equals 25. Take the square root of both sides. My x could equal plus or minus 5. Okay. Next thing here is we're going to solve equations by um, finding the variable that's inside of it already given a value on the other side of the equal sign. So what you need to do is isolate a logarithm expression on one side, and then what I want to do is I want to rewrite it back in standard form. So if we rewrite this back in standard form, I get 7 squared equals 3x minus 2. So this 7 squared is 49, which equals 3x minus 2. Add 2 to both sides, so it gives me what, 51 equals 3x. Divide both sides by 3, my x will equal 17. If I look at example B, I have what I can do is using my product property of logarithms, so I can say log base 6 of 3x times x minus 4 equals 2. And then what I'll do is I'll distribute that, so this goes x base log base 6, so it'd be what, 3x squared minus 12x equals 2. So if I rewrite that in standard form, I'm going to get 6 squared equals 3x squared minus 12x. 6 squared is 36, which equals 3x squared minus 12x. And this is basically what has become like a quadratic to us. So I'm going to subtract 36 to both sides to try to get one side equal to 0. So now I'm left with 3x squared minus 12x minus 36. I can reverse FOIL this, so I goes 3x, I got x, and this for this one it becomes plus 6 and minus 6. And if I use the zero product property, I get x equals negative 2 and x equals 6. Plug those back in there to see if we can check for any extraneous solutions. Both of these ones hold true, so I have x equals negative 2. I got x equals 6. And that is being able to solve exponential and logarithmic equations. Hope this helps. Until next time.